Hello, everybody. Good morning. Welcome to the URMA MX Boronite webinar here in Switzerland live. And yeah, we would like to welcome you. I'm Gianluca Barra, and this is Yuri Virs.
Hi, I'm Yuri.
Yeah. So just 2-3 information for the webinar. We will talk about MX Boronite versus MX Diamond. So where are the differences? Then we will do a comparison of cutting materials. We will talk about thick to thin chip milling strategy. And also we will speak a little bit about economic efficiency. And then the last section is technology in detail. There is a Q&A section open in the Teams. So if you have questions, please write them into the Q&A section. And then after the webinar, we will pick a couple questions and answer them. Perfect. So then let's start with the webinar, URMA Novelty MX Boronite. This is the new product we have. And let's start with a short video. Yeah, as you can see, MX Diamond and MX Boronite. So basically after the MX Diamond, the question of the market was pretty big for something else, for machining cast. Now we came out with it. As you can see here on the video, the lineup is now from 50 to 125 millimeters for each product. They can be assembled on standard shell mill holders, so you don't need any special tapers. Of course, please make sure to use a coolant-through version. And here, as you can see on the bigger sizes on the diamond, they are made hybridly with aluminum. And this is a very nice detail here of the run-out adjustment, which is performed directly on the machine to eliminate all the spindle errors. And then it's very easy to do the cutter change, as you already know from some of our other products. No readjustment needed.
All right, nice video. So let's start with some key points which will follow us through the whole webinar. The MX Boronite is a CBN-tipped carbide cutting ring. It's developed to machine cast iron, hardened steels, and powder metals. And we have a relatively high CBN content for best wear resistance in this tool. It gives you excellent cutting edge stability thanks to the solid carbide disc which carries the tips. And it has, as you have seen in the video already, a very easy actual run-out adjustment.
Perfect, Yuri, thank you. So here you see a little comparison about the MX Boronite and the MX Diamond. As you have seen already in the video, the Boronite is tipped with CBN and is made to be used in cast iron, hardened steel, and powder metals. You see the AP is more on the finishing side. This is also where the product has its strength. But we will also talk later about how can you also remove more material AP-wise. And then the MX Diamond, which is tipped with PCD with diamonds. And this is mainly used for non-ferrous like aluminum, magnesium, and so on, and plastics. So in here, of course, due to the softer materials that we are cutting, you can also use it for a heavier cut from up to 4 millimeters. So yeah, and next we will have Yuri telling you something about some cutting materials.
Thanks, Johnny. Yeah, we have already mentioned that there's two different cutting materials available in the MX series, PCD for the MX Diamond and CBN for the MX Boronite, and we thought it might be a good idea to touch all the different cutting materials available and also look into some of the materials that are machined with those different cutting materials, because there's a lot around. So on this slide, you see different materials with very, very different properties. On the top left, you have composites, where you have very hard and abrasive fibers in, for instance, a polymeric matrix, which can be very sticky. You see the nickel, which is very often used in nickel-based superalloys, which have very, very good thermal properties, but which are nasty to machine. On the bottom, you have chromium, which, when used in stainless steels, creates a very sticky material, which gives you a lot of build-up edge in machining. And then you have two oxides. On the right, you have the rutile, which is basically the oxide form of titanium. And on the left, you have aluminum. And all those materials have very, very different properties. So to machine those, you need basically the ideal cutting material. So what is an ideal cutting material, and does it exist? Well, an ideal cutting material would be hard and compression resistant, but at the same time, it also would be tough and bending resistant. You need thermal and chemical durability. It should be universal of use, because you've seen there's a lot of different materials around. It should be abrasion resistant. It should be cheap, of course, and it should be easy to machine, and it should have a reproducible behavior. Or, with other words, you're looking for the jack of all trades. And since the jack of all trades doesn't exist yet, we need to deal with a large variety of cutting materials. And just by comparing their mechanical properties, they can be easily grouped. So if you look at this plot, which you're seeing here, you have the hardness plotted over toughness and strength of the cutting material. And if you go to the very right, where it's very tough, you see the HSS. Very tough, but not very hard. And if you go to the other side, where the toughness is low, but the hardness is very high, you end up at the CVD diamond. And this is the whole range of properties you can find in a cutting material. And what's also interesting is that you have this huge block in the middle. The cemented carbide here in the middle, this covers a very broad variety of properties, especially when it's coated. And you know that from when you look into the ISO standard, you see that there's a lot of different material groups, and along with those material groups, you can attach the right carbide grade for your machining application. So let's pick the extreme ones first. PCD, that's the hardest cutting material we know to date, and it's particularly suitable for machining non-ferrous and highly abrasive materials, such as titanium alloys. Aluminum alloys are also copper alloys, and it's also nice for using it in polymers and fiber composites. That's the MX Diamond. For the MX Boronite, we picked the CBN, cubic boron nitride. It's the second highest hardness cutting material, and it's used for machining hard and brittle and also very abrasive materials, where conventional cutting materials stop working. So for hardened steels, for high strength chromium steels, PM steels, cast iron, and superalloys. And those two denominate the group of high hardness cutting materials. And everything which comes below that, ceramics, cermets, carbides, and HSS, are hard cutting materials, not high hardness cutting materials anymore. And they cover, again, a very, very broad spectrum of different materials. And they also touch the main materials from the other groups, like steels or stainless steels and superalloys, especially on the carbide when it's coated. So all those materials experience a lot of wear in the process. And just to have a brief look into wear and what does it mean, I've listed a few key points here. Wear refers to the gradual degradation of a tool during use. And it occurs due to high thermal, chemical, and also mechanical stress on the cutting wedge whenever it's in contact with the material you're machining. It creates increasing cutting forces and also geometric deviations from the workpiece when you manufacture it. So you get roughness increase, you get a form error, you can get dimensional errors. And ultimately it defines and reduces the tool's service life. And we differentiate three main groups of wear. One is abrasion. Abrasion happens always in machining, independently of the cutting speed. Then we have adhesion, which is like a form of welding of the workpiece onto the tool. You know this usually has build-up edge. And the third one, diffusion, happens at high temperatures when you have either cutting material from the insert leaving into the chip or material leaving from the chip into the cutting insert. Both can happen. And just keep in mind, machining always causes wear. And when we talk about diffusion and about temperatures, this is no joke, because temperatures in machining can be very high. If you look here on the right side, this is the MX Boronite machining hardened steel, and you see all those glowing chips flying out. High temperatures occur in machining. And typically, when you machine steels, the temperature in the cutting wedge is above 700 degrees Celsius. That's already very, very hot. Interestingly, the majority of the heat is being transferred into the chip and leaves the working space after the chip is cut off from the workpiece. And almost a quarter of the heat is transferred into the cutting material. So you need a very high thermal stability of the cutting material when you go into hot cutting applications. That's why we are using cubic boron nitride for the MX Boronite. As mentioned, it's the second hardest cutting material below. You use it for hardened steels, for cast iron, and also for nickel and cobalt-based superalloys. And it's chemically inert at high temperatures, especially against iron. And just if you do a little comparison down there, the hot hardness of a CBN is above 1300 degrees Celsius. For comparison, a carbide, coated or uncoated, usually deteriorates at 800 degrees Celsius. So that's significantly lower, which makes it less susceptible for high temperatures. So when you go into machining, we brought a little example here. So this is milling cast iron GG25 with a 95% CBN grade. And you might wonder, oh, this is a very high CBN content in the CBN grade. But due to the stability of the cutter, we will see that later, this is no problem for machining. So just look into the video here and see how all the glowing chips are flying out. Yeah, thanks. Let's summarize quickly. High hardness cutting materials are used for high performance cutting applications. They need to be perfectly adjusted to the machining process, so you cannot use the one-fits-all approach. Economical machining processes for today and for tomorrow, and you have the highest process reliability when you pick the right cutting materials, and of course the highest productivity and sustainability. So thanks. I hand over to Johnny.
Thank you, Yuri. Very interesting. So the next chapter is thick to thin chip milling strategy, because you can have the best product in the world and the hardest cutting materials, but you can even gain a little bit more tool life and productivity by using the right milling strategy independently of the tool. And this is what we're talking next in this chapter. So basically, there is a golden rule, and the golden rule is thick to thin chip. So you want to have a possibly thin chip at the exit of your cutter, and a more thicker chip basically when the cutter enters the material. This is proven to generate less vibrations and to have less impact on your cutting edge, basically. So, and let's have a look first on a little video how this looks when you're just going full AE, how the chip is formed in general. So as you can see, when the cutter enters the part, you have a very thin chip. It gets thick into the middle, and then it thins out again. And here you see what happens if you do it the wrong way. You have a very thick chip there at the exit, and here is a good example. You have a thin chip at the exit and a thick chip at the entrance. This is what you want to have, because this gives you a much better stability, so less vibration, as I already said, and it's a lot more healthy for your cutting edge. So let's have a look into the roll-in method, which is one of the most preferred methods to enter basically into a part. So here you see a bad example, basically just going into a piece with about 90% of AE. Here would be a roll-in method, but from the wrong side. So you see how the chip thickness is very inappropriate. And here you have a good example how you're rolling into the part with having a very thin chip at the exit and basically the maximum at the entrance of your cutter. Yes. So let's have a quick look here into the different strategies. So we have seen the linear strategy, which is just entering straight into the part, which is not ideal for vibrations and wear. Then we have the alternative, which is the one in the middle, which is the ramp method. This is already very good. You can see how the chips look, but it's not very smooth because it's basically an angle. So, and on the right you have the most preferred, which is basically a roll-in method where you are running basically on a row or on a radius. You're running into the part, and this generates an excellent entrance into the part. So next up, we will have a look at the forces, because we analyze them with the different features or the different methods. So let's check it out. You see here on the left side, we have the blue force line. This is with an MX diameter 63. And the red one is a competitor tool, also diameter 33. And what you notice is basically that you have a very high force in this midsection. This is exactly when the cutter basically is in full use. So it generates a lot of vibrations. Then you see the ramp version. It's already a little bit smoother. It's not as harsh. Also, the starting point, there is a little ramp also to the maximum force. And on the right side, the roll-in method, you see that the forces, both from competitor and ours, are significantly lower, so less vibration, better for the tool itself. But the conclusion here is basically what you can see is that nevertheless, if you're using linear ramp or roll-in method with the MX system, you have significantly less vibrations than the competitor tool. And this is already a very nice benefit. So here, that's the last slide of this section. Let's have a look into consistent cutting process. That's a video as well, just to give you an idea what would be very efficient here. So if you have a regular plate and you're just running lines over it, you see that every time you enter, you have not a very ideal chip thickness. Here is when you're using just a square pattern. Every time you change direction, you have again this thin to thick chip issue. So, and here if you can run with a radius basically instead of a sharp edge, you see that every time and the corner we have very thin chips, and this is the preferred strategy to have the most tool life out of the cutter. Also here another example, running over an interrupted cut with a fairly big cutter straight over it, which is definitely not healthy for the cutting edge. This is much more preferred, using a smaller cutter, running in a circular motion over the part and controlling the chip thickness. Yes, so this was it for the milling strategy. I hope that you have seen that this is a very important point because it really makes a big difference. You saw it on the spikes of the forces. They are very significant from one strategy to the other. But what we can say as a conclusion is also that with the IMAX cutter, you are always better fitted vibration-wise and stability-wise than with most competitor tools. This gives you the chance to run higher feed rates, more depths of cut depending on the material, of course, but overall gives you more performance with less vibrations. Speaking of performance, let's head into the next chapter, which is the economic efficiency. So basically, here you see a very regular style cutter that is on the market, which is usually cartridge style cutters. So it means they are independently mounted on a body and then basically adjusted on a presetting device. This is what you see on most tools in the market when it comes to finish and super finish with super hard or high hardness cutting materials. So where is the issue here? It is, of course, time consuming because you have to adjust every single tooth. This is one thing. And the other thing, you have to do it on a presetter. And guess what? There is a reason why it's called presetter and not final setter. So you cannot eliminate the errors of your spindle. So let's have a look. We saw that in the video before, how we do it, what our approach is, and our approach is to do this directly on the machine, because with this we can eliminate also the errors of your spindle and have the best possible axial runout. This helps to give an excellent performance in the cut. And of course, the insert change is quick and easy, which is even more essential on the Boronite because, of course, using it with cast iron hardened steel, the tool life is naturally significantly lower than with the diamond, which is used in aluminum. I guess this is very clear. So then let's dive in. Let's look at an example here. There we go. So this is a calculation example from the MX Boronite. You see it's a GG25 part. Number of components per year, it's 25,000 pieces. We took 120 euro as an hourly machine rate, and the rest I think is very clear. What is important to know beforehand is that these tools, they have a power consumption. In terms of the diamond on the right side, you see how much torque and how much power the tool needs depending on the AP that is used, and it can go pretty high. And on the left side, you have the AE-AP ratio. This is what I was telling you in the comparison before. You can run higher APs than 1 millimeter with the Boronite, but then you have to back up significantly with the AE. This is something important to know. So let's hop into the calculation example here. And basically, you can see we compared against the competitor. And again, we're talking about cost per part, cost per piece calculation. This is very essential for us because since the precision is all in our tool, of course, the tool cannot be as cheap as a tool where the precision has to be made by the customer. This is very obvious. But we can definitely perform with higher speeds, with higher feed rates, with a more flat surface, and this gives you overall a much better productivity, which lastly makes your part cheaper. And you can see this here in the calculation. We compared basically apples with apples. So same size cutter, same depths of cut, and so on. And at the end, you will see that we significantly can save money. In this example, it's over 65,000 euros. on a year, 20,000 pieces production, just because we can run higher speeds and also therefore higher feeds including with that. So yeah, this was it basically for this part. And now we're going to hop into technology in detail with Yuri.
Thanks, Johnny. Johnny, I really like the story you told with the presetter, because I think this is something which is not clear for a lot of people, that if you want ultimate precision in an application, it's not enough to go on a presetter. You need to adjust the tool on the spindle. And with the MX, it's particularly easy to do that. All right, let's go into the last block, technology in detail. We got a lot of feedback from customers who said, wow, this tool is surprisingly reliable in processes, especially in unstable workpieces and under difficult conditions. And we thought, hey, wow, that's the feedback we like to hear, because that's the best feedback you can get. But in the end, knowing is better than just hearing feedback. So we decided to go into a scientific study which was carried out with an external research institute to precisely address the functionality of our tools and figure out some of the process parameters which are really important. So we picked 2 tools, sent it to the research institute and said, well, go into an analogy test, measure process forces in different materials. That's one of the work packages we are going to show you. And the second one was, as Johnny already touched, the milling strategies, where we really investigated the influence of the milling strategy on the process stability. And what we did was we selected 2 tools, one MX, diameter 63, and we selected a competitor tool, which was exactly the same size and number of teeth as the MX. So 63 millimeters diameter and 100 millimeter diameter, 2 cutting materials, PCD and CBN on both sides, and the same number of teeth on both sides. And we said, well, test them. And the first feedback, which was already very nice, was even before they started machining, when they looked into the setting time, that they said, well, we need about 5 minutes to set up the MX Boronite and the MX Diamond, versus we need about 40 minutes of setting time for the competitor tool. So that was pretty nice. But now let's go into the work packages. AP1. So the setup which you see here is pretty simple. You have the MX standing still on a bore dynamometer. And from the top you have the spindle which rotates a workpiece. And this is pushed down into the tool. So the tool is stationary, the workpiece is rotating. This was done for the ease of measurement, although this is of course not a true application case. So the purpose was to figure out force and torque measurements with the smallest possible influence of disturbance and variables, and to obtain a force model of both milling tools. So we had different adjustable parameters. One was the cutting speed, the radial depth of cut, AE, which corresponds to FZ when milling, and the feet per revolution, which corresponds to AP when milling. And we did in total 7 cutting tests. And I'm not going to show you the individual numbers of the tests, but this is one of the major outcomes here. If you look into the linear force model, which was predicted here and then confirmed by the measurement, you can see a big difference between values you get from literature and values as they actually occur in a test. So the aim was here to predict the motor power and the torque during the cutting. And what you can see is that in the linear force model, you see a cutting force. This is predicted up here, and then if you calculate that with values from literature, you get into a calculated power of 36.3 kilowatts and a calculated torque of 18.3 Newton meters. And the actual measurements gave a significantly lower torque and also a significantly lower calculated power. So this is very important when you go into process optimization, because you can plan your application based on customer-specific processes. And another thing which was very impressive in this test was the stability of the cutter. So here we are showing you a high-speed video when machining cast iron with the URMA MX Boronite. And what you can see is that you have very homogeneous small chips flying out. And please also pay attention to the gap between the tool and the workpiece, this gap is not varying. So both are very, very stable, and the tool is not deforming upon the cutting test. And if you're comparing this now to the competitor tool, you right away see that under exactly the same conditions, the chips which are being cut are of various size. You have very small chips, you have large chips, and also if you look into the gap between the tool and the workpiece, you see that the width of this gap is varying. Sometimes you see a tiny bit of light coming through, and sometimes it's completely closed. This means that the tool is moving away. It's vibrating, and this causes you a bad surface. The second workpiece, we had a different setup. The tool was rotating and the workpiece was stationary. So this is more like actual milling. And the purpose of this experiment was to evaluate the influence of a different approach, of different approach strategies when you're milling. So we had adjustable parameters, and we did in total 12 cutting tests. And this is the outcome. So basically what you see here is the process forces in different directions, X, Y, and Z. The blue bars are for the URMA MX, here for the MX Diamond in this case, because it was a test in aluminum. The red bars are for the competitor tool. And you can see that the bars from the URMA MX are always lower than from the competitor tool. In total, approximately 20% less cutting force applied with the MX than with a comparable competitor tool. And if you go now to a cast iron, which was the second test we did, these results are even more pronounced. The MX applies significantly less force to the workpiece than the competitor tool, in the order of 50% with the linear approach. So this was very nice for us to see, because now we have real measurements which kind of nicely fit into the feedback we get from the customers, that it's very stable and applies very, very little pressure on the surface. And with this, we are already at the end of the webinar, and I think we conclude. So, the MX Diamond and the MX Boronite demonstrate low process forces under dynamic conditions. You have a superior process stability, we've measured that, we've proven it, compared to any competitor tool on the market. The technical benefit is that you have a very homogeneous and predictable cutting force, which ultimately creates you a reliable process. You have low forces and vibrations in the process, and especially the little vibration you get increases the part and the component quality significantly. We have a validated force model, so we precisely know how the tool works and how it can be applied with the customer application. And of course, as a perspective, those results form a basis for the integration of a specific tool solution in highly demanding applications in the end, either on unstable working environments, but also in fully automated process environments.
Very nice. Thank you, Yuri. So yeah, thank you very much for attending the webinar. It was a pleasure for us to give you this webinar. I think we showed definitely that the tool has significant benefits against competition, but also on its own, it's a high-performance tool that can solve definitely also a lot of challenges that we're facing today in the market.
Definitely, yes.
Very good. So let's go into the Q&A section here. And let's see what kind of questions did we get. So here we have one: is it possible to machine cast iron like GGG40, GGG50, GGG60 with the MX Boronite, or is it only gray cast iron? So I would say with the grade that we have right now, this grade is extremely well suited for gray cast iron, but it does not mean that it cannot be used in ductile iron as well. Yep. Of course, in ductile iron, usually the benefits in general of CBN are not as high as in the gray cast iron, yeah. Right, Yuri?
That's true.
Okay. So let's see. Actually, next question. Actually, we can use CBN for finishing turning operations. will it be possible to do finishing milling operations with Boronite cutter where it's not possible with ceramics? I don't understand exactly in which material, but of course, it is mainly a finishing tool.
Yeah.
It's not meant to take away 10 millimeters of material, so it is meant to do finishing, definitely.
Yeah, especially due to the low vibrations you see in the process. This is kind of predefines it for using it successfully in a finishing applications. And also with the adjustability where you can really get the best out of your surface.
Yeah, that makes absolutely sense. So there we go. What is calculation, I guess, calculation method to define the radius value for the entry on the face milling? So basically, it is half of your AE. This is basically the radius you're using to program it and enter into the part. Good. So, are you able to retrofit Boronite inserts? Well, that's an excellent question. If we are able, it's not a question of capabilities. It's more a question of an economical view. So, as you can think of, the blank is the cheapest part basically in the whole cutter, because there goes a lot of labor into the cutting disc with EDM laser or whatever technology we're using. So this is where the most of the money basically sits. So are we able? Yes. Does it make sense for one piece? No. It makes sense further down the line if we can bulk up some inserts. If you have a high consumption customer, then I think we can definitely talk about, and then it makes also sense shipping wise, cost wise also for the end user. You agree, Yuri?
I agree fully.
Perfect. Do you want to go with the next question? That's a long one.
So could you please inform me about the theoretical surface roughness achievable with these machine heads? I understand that actual roughness depends on various factors, but I'm interested in knowing the theoretical values that can be expected. Actually, we're running a study on that at the moment to give you really detailed information about that, but as I've shown on the, was it the fourth or fifth slide in the presentation?
Can be, yes.
Yeah, approximately when we were milling the cast iron. So this was between 0.1 and 0.4.
Yeah.
So this is a value which you can expect when you're machining cast iron.
Yeah, I definitely agree. If you have a lot of pinholes, probably you're more towards the 0.4.
Sure.
But if you have a good cast, 0.1 or 0.15 RA is not unheard of. I mean, we achieved even an RZ values around 1.5 to 1.8. So you can achieve very, very nice finishes. But of course, in cast, talking about surface finish is, walking on a frozen lake. You never know what's going on because it depends so much on the quality of the cast.
Yeah. So if you have a high quality cast or like a white cast iron, which is pretty hard, you achieve RAs in the order of 0.1. We measured that from a customer test. I remember that value because I was there when we did the measurement. So this was easily achievable after adjusting the tool. Okay, I'll also take the next one. Are you planning on more cutting materials? Well, this is very easy to answer. Yes. You've seen the list of cutting materials which I've shown before. There's a lot of different materials you can use. And of course, we are working with those materials, yes.
Perfect. Shall I do the next?
Sure.
Okay. So we have, the next one is based on your experience, how much adjustment range do customers typically have on the machines? Specifically, how adjustable are your machine heads? That's an excellent question. Thank you for this. Of course, it depends a little bit on the size of the cutter. The smaller the cutter, the less you really can and hopefully have to adjust. The bigger the cutter is, the more wiggle you have. So on the Boronite, on the smaller heads like the 50 and the 63, we are more talking about a range of 2-3 microns, more or less. And on the bigger sizes, we're talking more about 5, 6, maybe 7 microns of axial runout that can be adjusted. Honestly, your machine should not have a whole lot more, because you have to understand, I mean, it's not the axis, it's really planarity or perpendicularity at the end, if you compare it to your spindle, that is off. So if you are there like 10, 15 microns, I don't know if I would use that machine to really do nice finishes. Huh?
I mean, after running a crash, you probably should rather do a service than trying to adjust the actual runout with the Amex and keep on machining. So
exactly. So it is meant to basically get rid of the little bit that really makes a difference, of course, in the part. So let's say it's a couple microns to summarize it.
Yeah.
All right. I think we have the last one, Yuri. That's for you.
So can I use MX Boronite inserts on an MX diamond body? Well, although the interface is technically the same, you cannot for different reasons. First of all, the MX Boronite has a different pitch than the MX Diamond. Then also it's a matter of the construction of the cutter body, where with the MX Diamond you have a hybrid construction, whereas with the MX Boronite it's a steel construction, so it's not a hybrid block. We need this for the higher rigidity and also the higher process forces during the cast iron machining, for instance, so you cannot fit that. And it's also a Poka-yoke principle, so you cannot just take a Boronite insert and put it on the diamond head. It will not fit.
Okay, so there is something that prevents it.
Exactly. So this was made on purpose, that there are no mix-ups.
Very good. Very good. Perfect. Yeah, I think we reached the last questions, right? There is no more. Okay, perfect. Then I would say thank you very much for the attention. Enjoy the day, and hopefully you took something interesting out of that presentation and are hungry to use the tool in your application and solve your challenges.
Yes, go for it. And we're always here to help you.
Thank you. Have a good one.
Bye.
Bye.
Take care.